So, as the main topics of this presentation, we'll talk a little about automated machine learning. After that, pipelines and ensembles. Bring the definition of the technique Auto-CVE with dynamic sampling. Experiments, research perspectives and conclusions, and references. So, beginning. Machine learning is the trends today. I think you already know that. But building the solution is not a trivial task. The person responsible to building the solution needs to know where to apply the technique, so the domain, and needs to know how to apply the technique, so the machine learning context. But despite this complexity, many steps may have some potential for automation. Hyperparameter search and algorithm selection are good examples already in the literature in this context, okay? In addition, there is the no free lunch theorem. It states basically that all models have equal performance when compared across all possible data sets. This means basically that there is no silver bullet, there is no single model that have the best performance in all cases and domains. So, automated machine learning arises basically from this context. When you have so many possibilities to search and no single rule for how to choose. So we need a technique that can search across the search space to find for us the best models, okay? Also, when we're talking about Auto-CVE, we're talking about distinct steps as cleaning the data and finding hyperparameters. But in here, we focus on algorithm selection and hyperparameter search. In addition, we're talking here just about classification tasks, okay? Following, pipeline is an expression that will be heavily used here. Pipeline can be defined as a sequence of operators applied in a dataset to obtain some response. So, besides that core traditional machine learning technique, a decision tree, for example, a pipeline also includes scalar operators, transformation operator as log, exponential, etc., feature selection, among several others. This inclusion of preprocessing is needed because preprocessing steps may have a large impact on behavior and performance of machine learning technique, and its choice is very specific for each technique. So it makes sense that we include the definition of these operations together with the machine learning core. In the same sense, when we're talking about pipelines, we include hyperparameters as well, okay? So now I'm talking about ensembles. Ensembles are the combination of single machine learning models and to boost the model performance. The basic idea here is that when we combine the models, the weakness of each one is compensated by the strength of the others. So something like a wisdom of the crowds, okay? And the thing about ensembles is that they are really good options when looking to improve our model performance, given that they effectively have a better performance than single models. So it's common that we have a better model with ensembles, and it's easy to combine models. As example, we can just gather all predictions and elect the most voted class in a classification problem. And if we search for a good machine learning model, we are already passed through several possible ensemble components. In this sense, ensembles can be a good approach when we are in the AutoML context. Basically because they already have a good performance. And if we're looking for good ensembles, we just need that these components have a good performance themselves and they are sufficiently distinct, okay? But in AutoML, diversity in the search is not priority normally. The traditional techniques just look for the best single model and combines what is found in the procedure. So if we're looking for ensembles directly, can we have a better performance? So now talking about the Auto-CVE, our idea is to focus on building ensembles element of interest. In this sense, the Auto-CVE uses an implementation of the Coevolutionary framework, where we have two populations. One of these populations is composed by pipelines to be used in an ensemble, the single model that will be aggregated. And the other population is composed by ensembles, in which we will search the best ways to combine the pipelines involved in the first population. And as these pipelines are evaluated based on their performance on the ensembles, have these two populations interacting with each other. Okay, following, we use the traditional structure in coevolution. We give one step per population. The population of the components is evolved through a contextual genetic programming, while the ensemble population uses genetic algorithm. And we run on some stock criteria, get the best ensemble at the end. So the idea is pretty simple. Here, just to give you some vision of the algorithm. First, we initialize the population, loop with each population performing one step per generation and interaction, and at the end return the best ensemble. Okay. To give you now some details, first talking about the component's evolution. Here we use a niche scan to guarantee some diversity, following that idea of maintaining diversity in ensembles. Crossover and mutation is done as usual in CFGP, and we store the predictions of each component to evaluate the ensemble. So we do not need to train and test each component to every ensemble that you use it. Okay. And at the end, the fitness of each pipeline is just the mean performance of the ensembles where this pipeline is part of. About the evolution of the ensembles, use the same niche scheme here to maintain evolutionary procedures similar. Mutation and crossover has some small modifications when compared to the traditional binary operations, and the features of each ensemble is just the performance of the ensemble itself. If you have a time the performance of two ensembles, we have a second criteria when you just get the smaller ensemble. So, all this procedure until now is valid for both evaluation through cross-validation and holdout. But to use the holdout, we change a few things. First, we need to employ dynamic evaluation. So, for every generation, we resampling the training test sets and report for evaluation in all the population. The idea is to restructure the overfit to a single generation. And even we lose some good pipelines because it has a high variance, the population as whole will converge. Also, in the last generation, we can perform just a single cross-validation procedure to choose the best ensemble. In this sense, we can greatly reduce the evaluation time and yet control the overfitting level in the procedure. Here, just to show you the schematic of this procedure. We pass the dataset to the Auto-CVE, and after that, we have a loop. Random draft for each generation, train test sets, and apply to all elements in the generation, the population, and the offspring. Ensembles will just use the prediction in the test portion of the dataset, but in your test, this was not a big problem, okay? So, to verify the effects of using this type of strategy, we perform a set of experiments using the benchmark proposed in Barbosa and Helio. We compare here the Auto-CVE using both cross-validation and holdout, includes the TPOT library as well. Also, we use the balance accuracy as a metric to deal with unbalanced datasets. And as a stock criteria, we set 90 minutes or 100 generations for the three techniques. So first, measuring the amount of overfitting in the evaluation procedure. In here, we test model of each generation of the Auto-CVE and use the difference between the inner evaluation of the algorithm and the evaluation made in external sample. This is the amount of overfitting we're talking about. So looking to the results, we can see that the use of cross-validation in blue have a small amount of overfitting in the beginning, and it grows as generation pass. But when looking for holdout with dynamic sampling, we have indeed a higher overfitting amount in the beginning, give it higher variance, but the overfitting stays in the same level for all the evolution. And in fact, the dynamic sample has a lower overfitting measure in the final predictions, lower than the cross-validation clues. So what you can see here is that the use of a holdout with dynamic sampling has a great effect on control the overfitting. Also, the use of cross-validation only in the last generations has a positive effect in the Auto-CVE as well. Okay, here, just summarize what I said. I not wasting a huge amount of time here, okay? Now, looking for the performance results, here we plot a box plot with the 10 runs of each algorithm in the 15 data sets. What you can see here is that there is no huge difference in any data set. In fact, the largest difference is here in this data set, but there is no clear pattern of a better technique during all these data sets. So some comments here. The first is that all the techniques are pretty similar with no large gap, and you perform a Friedman test to verify some statistical difference in this test fail, which goes toward this conclusion of similarity. Okay. Now looking for the computational time, what we see here is that there is a clear winner in this metric. The two versions of Auto-CVE are faster than TPOT in all executions, ignoring when we reach the time limit because this brings some anomalies, okay? And the use of holdout is faster than cross-validation as well. In fact, it's at least 2 times faster, okay? Again, just some comments. It's basically I said earlier. But summarizing, what you have here is that Auto-CVE in both versions has state-of-the-art performance, similar to the TPOT, but is significantly faster than TPOT. So Auto-CVE is a promising approach to AutoML, and dynamic sample shows as a good strategy to reduce computational time and controls overfitting. Now, talking about some research perspectives, the Auto-CVE is a proposal in evolution, and we think there is much room for further improvement. In this sense, we can think about some measures to reduce the computational time even more. One option can be using a dynamic population size and reduce it as the evolution goes. And other option can be penalize expensive pipelines based on the computational time. Should they just discard pipelines which needs more than 60 seconds? To improve the performance, we can think about the addition of other operators and using meta-learning in the initialization procedure of the populations. For the dynamic sampling holdout, given its good results, we can think about applying to other AutoML approach as the TPOT, given its potential to reduce computational time. At the end, some conclusions. Auto-CVE achieves results comparable with a state-of-the-art algorithm, the TPOT, and with much less computational time required. In addition, Dynamic sampling shows as a great option to reduce computational time and maintain performance. And how this proposal can be further improved, and everyone's suggestions are welcome. Find some references. Thank you for your attention.